the homework?
I have a question about it.
Sure.
So when you write your final answer for like components, do they still have units on them or are they just like raw numbers?
They should have units.
Okay.
So if you want to find the components of a vector that has that is 10 meters per second square, the components in X and the components in Y also have meters per second square units. They should have the same kind of units. So if anyone had any trouble uploading the homework, they can always take a picture of the homework and then upload it to me, send it to me on an email. It's not ideal because then the emails get gonna be buried by the end of the weekend, but I'll try to keep a track of them. And if you don't see the grade of your homework in the next couple of days, just send me an email and just remind me. Yes.
So you don't want any physical copies at all? You want everything uploaded to Canvas?
No. There's a lot of people that they have given me the hard copy, and that's fine. Like if you are here today, you can give me a hard copy. Or if someone is not on Fridays, they can just drop the homework on my mailbox on the dean at my office, and that's also perfectly fine. But I know that some people have been trying to upload the homework, and for some reason doesn't allow it. So they can just take a picture, and that will be fine. Okay. Any questions about the homework? Everything makes sense? For the people in the chat, everything makes sense? Yes. Okay. So, yes, Christopher, yes, you can email me the homework. It's not ideal because I tend to misplace those, but you can. At least that way your homework won't be late. Okay. So the last thing that we talked on Wednesday was basically talk about static and dynamic equilibrium. And static and dynamic equilibrium are very specific conditions of what happens when the acceleration of an object is zero. So when the acceleration is zero, it can be because we have constant velocity, or it can be because it's not moving. Okay, so in either of these cases, because the acceleration is zero, where we end up is that Newton's second law is going to look like the force is going to be equals to mass times acceleration, but this acceleration is zero. So then we have, oops, that the sum of forces is going to be equals to zero. Okay, so they look the same regardless. This is going to be the dynamic equilibrium, and the bottom one is the static equilibrium. They look the same in terms of equations, but they have different meanings. Like in the first one, the object is still moving. It's just going to be at a constant velocity. In the second one, the object is not moving at all, and the object's not going to change that state. So I think some of you put it in one of your quizzes. When an object falls, like for example, a skydiver, start falling, and then the velocity start increasing really fast, and then there's going to be a point in which the drag is so high that the diver is going to have zero acceleration. Now, that's called terminal velocity, and that's basically the maximum velocity that an object can achieve by falling in free fall. Now, just because acceleration is equal to zero doesn't mean that the guy is not falling anymore. It just means that the velocity is going to be constant all the time. So there are different ways that we can calculate acceleration, and I haven't talked about acceleration and velocity in terms of equation very much, but one really quick equation to calculate acceleration is to understand the acceleration is the change in velocity with respect of time. Now you remember this delta operand. This is a mathematical expression, and it basically means final state minus initial state. So this is the same as saying my final velocity minus my initial velocity divided by time. So if we have an example saying, well, I'm going to have a pitcher that is moving his arm, and the arm goes from rest from 0 meters per second to a maximum of 20 meters per second in 3 seconds. So how fast is the arm moving? So we can say, well, the acceleration is going to be, final state is going to be 20 minus initial state is going to be 0 over 3 seconds. That takes that change in velocity. That's going to give you 6.66 whatever. Yeah. Meters per second square. Okay. The same way from this equation, if you have the acceleration and you have the time, you can calculate what is the change in velocity and so on. Okay, we're gonna do a couple of problems involving acceleration and the information is gonna be given as a change in velocity. Grace, you're falling asleep. I saw that giant yawn. We're gonna do a couple of problems, but I'm not gonna go really deep into calculating times and velocities and stuff like that. We're gonna do that later, okay? So we have this case for equilibrium, and we call this equilibrium conditions when the acceleration is 0. And we have these two cases that we have talked so far. Now, the last thing we need to find out is, okay, what happens if the acceleration is different than 0? So if the acceleration is different than 0, then Newton's law cannot be simplified, and then we'll have that the sum of forces is going to be equal to mass times acceleration. And we call this a dynamic state. Meaning that it's constantly changing, and the velocity is going to change. Now, when acceleration is different than 0, there are 3 things that can happen. 1, the velocity increases. 2, the velocity decreases. And the third one is that the trajectory changes. Okay, so if you go in a straight line and then you go into a curve, that implies acceleration. If you go in a straight line and then you just go into a different angle, that implies acceleration. We tend to think of changes in acceleration just as changes in velocity, but that's not true. This is incomplete. When you change a direction, if you're going into a curve, if you're driving your car and you're doing a curve, your acceleration is changing. And if you going up and down on a rolling hill, that also implies a change in acceleration. So every time you see an object changing directions, every time you see an object doing something other than moving in a straight line at a constant velocity, is because you have an acceleration. Okay? So we call this a dynamic state. And I'm going to do a quick example of this. And it's going to be very similar to the last problem that or one of the problems that we did on I don't know when, one of the couple of days ago. The one of Dumbo's mom. You guys remember that one? Have you seen Dumbo, Alex? Do you like Dumbo? Did you cry when you were a little kid about Dumbo's mom? No? How can you not cry when the mother's being taken away? Did you cry when Bambi died?
No, my sister did.
But you didn't cry when they killed Bambi's mom? No? You hunt?
I do hunt, but as a kid, I was like,
It just happened.
it's like
It's very gay.
I used to read biology books, so I was like, and
Did you hunt with rifle or with
bow.
bow?
Yeah,
Oh wow.
I think it's cheating when you shoot with a gun.
when you start hunting with a knife and just like just close to the animal, that would be cool. What? Okay. So we have Dumpus mode again. And here we have Alex pulling, taking away Dumbo's mom away from Dumbo. I'm not gonna say that she's happy, but she's definitely not crying. Unlike Dumbo's mom. It's a big tear. So we're gonna assume that Dumbo's again has a weight of a mass, sorry, of 1,500 kilograms. We're gonna assume again that we have the same friction that we had before. I think was 300 newtons. So I'm gonna have a friction here of 300 newtons. The angle is still gonna be 20 degrees. Okay. But now, so last time when we were solving this problem, what we said was, okay, we're gonna be moving this elephant at a constant velocity. So now in this case, what I'm gonna say is that when Alex started pulling the elephant was at rest, and she started dragging the elephant, and at the end, it went from 0 meters per second to 12 meters per second in 5 seconds. Okay. So we're gonna do this problem step by step. So the first thing that I want you to try is to do identify the forces that are on the elephant, and then draw the free body diagram. Okay, just start with the free body diagram. That's fine. Oh. Okay, so I think pretty much everybody got the right free body diagram, and it looks something like this. So you're gonna have the weight pulling down. So you're gonna have the weight. You're gonna have friction pulling backwards. Then you have the tension on the rope. That's what we want to find out. And then we have the normal force. Okay, so if you compare this free body diagram with the one that we did last time, the free body diagrams are exactly the same. Okay, so the free body diagram by themselves, they cannot tell you if you are dealing with a static equilibrium or a dynamic problem. You need to look at the text of the problem. You need to look at the setup of the problem to try to find out those information. So we can calculate the acceleration in this case, and I'm going to calculate the acceleration. So the acceleration is going to be, oops, a change in velocity divided by time. So it goes from 0 meters per second to 12 meters per second. So this is going to be my initial velocity, and this one's going to be my final velocity. So I'm going to have 12 minus 0 over 5. That's going to be, Kayla, what was your answer?
Oh, it was 2.4.
2.4 meters per second squared. Okay. Now, Tatum, did I pronounce it correctly? Tatum. Okay. In which direction is the elephant moving? To the right. Along what axis? The x-axis. Is it moving in the y-axis? No. So it's not moving in the y-axis. All the displacement of the elephant is along the x-axis. So this acceleration over here is an acceleration in x. In the y direction, there's no displacement. And if there's no displacement, there's no velocity, there's no change in velocity. And if there's no change in velocity, there's no acceleration. So in the y direction, we have that the acceleration in y is going to be equal to 0. Okay, so when we set up our equations, we're going to have two different equations, one for the x direction and one for the y direction as usual, but they're going to look a little bit different. So for the x direction, we're going to have that the sum of forces in x are going to be equal to mass times acceleration in x. And in the y direction, we're going to have that the sum of forces in y is going to be equal to 0. So in the x direction, we have a dynamic problem. And in the y direction, we have an equilibrium problem. And this is very common to see in these kind of problems, that you have the displacement just in one axis, and in the other axis, it doesn't change. You just have to be careful that you don't confuse that this acceleration is only in the x direction, that there's no acceleration in the y direction, and that they have two different set of equations. Okay? Okay, make sense? Okay. So I'm gonna try to solve for the tension. I'm gonna go for the x direction. Okay, and in the x direction, what forces do I have? Hina? What forces do I have?
You have friction going one way, and then you will have the tension in the other direction.
I have the friction on one side. I'm also going to have the x component of the tension. The x component of the tension, and all those together are going to be equals to mass times acceleration in x. Okay, my friction is going to be 300 newtons, but it's going in the negative x direction, so it's going to be negative. So it's going to be 300 newtons. My tension, I don't know what the tension is, but I know that it's only going to be the x component of whatever tension I have. So it's going to be T cosine of 20. And then the mass is the mass of the object being accelerated. In this case, it's not the mass of Alex. even though she's also moving, I'm not solving the problem for Alex. I'm looking at the elephant. I'm looking at the forces of the elephant. So I'm gonna care just the mass of the elephant. So this is gonna be the mass of the elephant times the acceleration. That is gonna be 2.4. So this is 1500 times 2.4. Okay. So from here, I can try to solve for the tension. The tension is going to be 1500 times 2.4 plus 300. Tension is going to be over cosine of 20. And I got 4,150.3 newtons. Yep. Make sense? On the back? Your name? Michaela? Okay. Does this make sense? Okay. So, so we solved the x direction. We solved for the tension. I'm gonna try to solve for the normal force. So again, for the normal force, I'm gonna use the equations in the y direction. And I'm gonna redraw the free body diagram because it doesn't fit in the page anymore. So I'm gonna have weight, friction, tension, and the normal force. So in the y direction, I have that all the forces are going to be equal to 0. All the forces in y are equal to 0. So in the y direction, I have 3 forces. I'm going to have the normal force. I'm going to have the y component of the tension. And I'm going to have the weight. And all of these are going to be equal to 0. Okay. The normal force, I have no idea what is the normal force. The tension, the y component of the tension is going to be positive. So that's going to be the 4,150.3 sine of 20. That's going to be the y component. And the weight is pointing down. The weight is going in the negative y direction. So that's going to be negative. That's going to be 1,500 times 9.8. And that's going to be equal to 0. So from there, I can solve for the normal force. Oh, sorry, Sylvia, I didn't see your message. Yes, Haley is correct. The friction is negative because it's in the opposite direction. So it's pointing in a negative x. So this will be 13,280.5 newtons. Yes.
Where did the 9 9.8 come from?
So the way we calculate the weight is going to be the mass of the object times gravity, and the value of gravity, or the acceleration caused by gravity, is going to be 9.8 meters per second squared. That's a constant. It changes depending on where you are on Earth, but we're not going to deal with those details. So you can assume 9.8. Those of you that are doing the SAT or the SAT, no, it's the SAT, the MCAT, I think they run it up to 10. Like, so they always assume the gravity is going to be 10. Because I don't think you're allowed to have a calculator. So just assume that it's 10. Yes.
Why did you use sine for the tension?
So for here, what I'm trying to do is to calculate the y component of the tension. So this is going to be my 20-degree angle. So the y component of the tension is going to be the opposite side. So I will need the sine of the angle. Yep. For the people in the chat, if you have a question and you write down on the chat and I don't answer right away, just you can unmute your phone. You can unmute your mics and just ask away. Don't be shy.
I'm confused. I understand why you use sine of 20, but I'm confused on why you used the x component for ty in front of sine of 20.
Oh, so I'm not using, this is not the x component of the tension. That's the magnitude of the tension. That's the size of the hypotenuse. So if I go back, this t cosine of 20 together is the x component. But when I'm solving and I'm divided by cosine of 20, this t alone, that will be the magnitude of the tension. So what I'm doing here is multiplying the magnitude of the tension or the size of the hypotenuse times sine of 20 to calculate the y component. Does that make sense?
Yeah, that makes sense. Thanks.
Okay. Any other questions? Are you sure? Okay. Now, something that you may be able to observe is that this tension over here, because it's pushing up, it's kind of lifting the elephant a little bit, not much, just a little bit. And as a consequence, the normal force is different than the weight. In many problems, if you have a mass and it's just sitting on a surface, you're gonna have the weight and you're gonna have the normal force. And if there's nothing else, then you're gonna have that the normal force is gonna be equal to the weight. But if you have a force pushing down, a hand pushing down, then the forces that are going down, you're going to have, now it's going to be the weight and also going to be the hand. So if you calculate the normal force, it's going to be higher than the weight. Okay, the same way that if you try to push up, if you're trying to lift the object a little bit, or if you're pulling with a rope, part of that rope is going to kind of lift the object, even if the object doesn't really detach from the floor. So as a consequence, the normal force changes, and that's relevant. We're going to see later today that the value of the normal force actually affects how an object is being displaced. Now, you can modify the value of the normal force by pushing down or pulling up of an object, either at an angle or completely perpendicular, but also it can change when an object is in a tilted plane. So if you have a box on a tilted plane, and I'm gonna say that this is 25 degrees. And I'm gonna assume that there's a friction here, but there's no displacement. Okay, so I'm gonna have gravity pulling down for the weight, and I'm gonna have the normal force perpendicular to the box. And what I want to do is calculate the normal force. So if I put this in a free body diagram, and I'm gonna say that the mass of the object is 10 kilograms. Okay, so from that, my free body diagram is gonna look something like this. Okay, that's it. So I'm just gonna work with the y direction. I'm just scared right now about the normal force. This angle is gonna be 25 degrees. So in the y direction, I'm only gonna have two forces. I'm gonna have the normal force, and I'm gonna have the y component of the weight. The normal force is what I want to find out. The weight is gonna be pulling down, so it's gonna be negative. And the weight is gonna be the 10 kilograms times gravity, 9.8. That's the weight. And because we need the y component, that's gonna be cosine of 25. And that's gonna be equal to 0. So the normal force will be 10 times 9.8 cosine of 25. That's gonna be equal to, oops. Will be 888.1.2 newtons. Okay, so if you compare this normal force with the normal force, if we have the same box sitting down on a flat surface, and this will be again the same mass, 10 kilograms. In this case, the normal force will be 980 newtons. Yeah. So as you increase this tilted plane and the angle becomes larger and larger and larger, the normal force is going to decrease. The minimum value that you can have for a normal force is that the normal force has to be bigger than 0. You cannot have a normal force or larger or equal than 0. You cannot have a negative normal force. If you have when the normal force is equal to 0, it basically means that the object is not longer in contact with the surface. And that's a way to check if an object is in contact with the surface. If the force is enough to lift an object, is to look for the value of the normal force. And if the normal force is, you get with a negative value, it doesn't make any sense. Or if you end up with 0, at the moment it goes to 0, that means that the object is not in contact with the surface anymore. Okay. Same thing happened with tension. The tension of an object cannot be less than 0. If you have a negative tension, basically it's like the rope is kind of folding and or you're trying to push with a rope. The tension is always going to have to be positive. Okay. Make sense? Ish. Now, why do we care about normal force? Well, the normal force. Don't go. Oh. So sad when they leave in the middle of the class. The normal force, the reason that I care about the normal force is because there are two quantities that depend on the normal force, and that is friction. That is friction, sorry. But we have two kinds of friction. One is called static friction, that we call F sub S. And the other one is what is called dynamic or kinetic friction. And we call that F sub K. Okay. So imagine that you are helping a friend to move out of his or her apartment, and you are trying to move a piece of furniture, and it's kind of big and heavy. It's supposed to be a sofa, but it looks more like a piano. But anyway, you get the idea. You try to move this object, and it's really, really heavy. And imagine that instead of having a nice flat surface, you have kind of like a carpet or something that is even makes it a lot more difficult. So you are pushing with your friend. Right now, I just want to draw one person. You push, and that thing doesn't move. And you push a little bit more, and it doesn't move at all. And then you push really, really hard, and that object starts moving. Okay? So while the object is not moving, you were increasing your force. And somehow friction was enough, or friction was able to match your pushing force in such a way that at the end, the furniture was not moving. Okay? So that's what we call friction force. That's what we call the static friction force. So the static friction force happens when the object is static, and the friction force increases as you increase the push of the object. So static happens when the object is not moving. Static friction. Doesn't move. And the static friction increases as you push. Okay, if I were to draw it in a graph, if I have here applied force, newtons, and here I have friction, also newtons, it will look something like this. If I push with 10 newtons and that is not enough to move the object, the static friction is going to be 10 newtons. If I push with 50 newtons and it's not enough, the static friction is also going to be 50 newtons. So it goes one by one, 1 to 1. So it's going to be a straight line at 45 degrees. You start pushing. Eventually, you're going to reach a threshold. And that threshold is going to be your maximum friction, your maximum static friction. When you reach that threshold and the object starts moving, what happens to the friction is that the friction is going to decrease, and it decreases sometimes a lot. So it's going to be a drop in the value of friction. And then as the object moves, it's going to start moving with a constant friction value. Regardless of how fast or how hard you push, the friction is going to be constant. So it's going to look like this. You're back. Okay, so this first area, this is what we call the static friction. And the static friction is always going to go from a value of 0 to a maximum value. And this maximum value, the way we calculate it is by using a coefficient factor that is called the static friction coefficient factor. And is letter mu sub s times the normal force. And this second area over here, this represents the kinetic friction. And the kinetic friction is always going to be constant. And it's going to be calculated by using another coefficient that's called mu sub k, times the normal force. Okay, this coefficient, mu k and mu s, are adimensional. Most coefficients are adimensional as well, but this one in particular is adimensional. And mu k is always going to be smaller than mu s. Okay, so for example, if you have, there's not an easy way to calculate the values of mu k and mu s. Actually, I don't think there's any equation that you can just put different characteristics of the materials and it will give you the value of mu k and mu s. Usually, these coefficients are obtained via experimentation, and in engineering you have books with tables of different coefficients. So for example, if you want to know the friction coefficient between rubber and concrete for tires. So rubber and concrete, the mu s is around 1.0 and the mu k is around 0.8. I think your book has a couple of tables. So if you have for motors and engines that you have pieces of metal sliding with other pieces of metal, so you have steel on steel, and you have some kind of lubrication, the mu s is 0.5 and the mu k I think is 0.1. And if you have ice, then you have like 0.1 here and 0.3 on mu k. So that's more or less to give you an idea where the what values to expect for mu k. Funny thing, the lowest value of friction coefficient ever registered has a value of mu s of 0.001. And that's the synovial fluid. So those of you who have taken